Hello, my name is Melissa Gonzalez and I will introduce the presentation. Although we know that aerospace engineering is relatively new, there is a lot of information available of its areas. Some of these areas are thermodynamics, resistance of materials, telecommunications, and the topic that we're going to talk about, dynamics. The in-depth study of dynamics on engineering, it helps a lot on operation aircrafts. In this presentation, we are going to focus on the prediction of trajectory on aircraft, the design and importance of reaction wheels, and the dynamics on the improvements of solar panel arms.
Hello, let me introduce myself. My name is Francisca Jara. I will explain trajectory prediction and its respective analysis. Machine learning is relevant to rocket vehicles during space launches as it provides online trajectory planning using models that translate system control, ensuring the safety of the spacecraft, and avoiding failures that can occur in complex environments. One of the methodologies used is neural networks, which dynamically adjusts spacecraft trajectory and orbital parameters in real time. This enables instantaneous data processing and, therefore, accurate results when autonomously executing orbital trajectory maneuvers. Figure 5 represents a deep neural network. To better understand the dynamics of space engineering and rocketry, the launch of a projectile to intercept an asteroid is proposed, analyzing the moment at which both bodies will collide. As shown in Figure 6, a free body diagram is established, where point B refers to the asteroid moving at a constant velocity v0, with an inclination angle of 30 degrees, heading directly toward point A, which refers to the city, with horizontal and vertical distance of L and H respectively. A projectile is also shown at distance L from the city, following a parabolic trajectory to intercept the asteroid. A parametric model is proposed where it is assumed that the projectile has a parabolic trajectory with an initial angle theta. The asteroid moves in a straight line and both will collide at a time t, using theta as a constant and ignoring free air friction. First, we establish our reference frame R in parentheses t represents time and R represents position. If we derive r in parentheses t, we have that velocity in parentheses t equals r1, with r1 must represent velocity magnitude and direction, so absolute value r1 equals v0. By observation for free body diagram, we have r0 and r1. By substituting these two vectors in the parametric equation, we can describe the asteroid trajectory. Through a free body diagram of the projectile body and Newton's second law in the y-axis direction, we know that summation force y equals mass multiplied by acceleration. Said expression can be solved by integrating twice with constant 1 has value constant 1 equals v0 multiplied by sine theta. By applying initial condition, the equation for y in parentheses t results less 1/2 multiplied by gravity multiplied by t squared addition velocity 1 multiplied by sine theta multiplied by t. For the x-axis, we will do the same process of applying a free body diagram and Newton's second law. Second derivative x to respect t, integrating, obtain constant 1, where Constant 1 corresponds with the initial condition horizontal speed. Constant 1 equals v1 multiplied by cosine theta multiplied by t. And constant 2, the initial x position, x equals 0, therefore x in parentheses t equals constant 1 multiplied by t addition constant 2. If we can parameterize the projectile trajectory, this results in r in parentheses t projectile equals function x and function y. Now, if we assume both objects collide in a time t, we can equate both trajectories, which results in position asteroid equals position projectile. If we represent this vectorial equation with a 2-bit system, and the system of equation is solved by solving for t and obtain the time at which both bodies collide.
Hi, I'm Oscar Merino, and next I'll be explaining how dynamics is utilized in the designing of motion and attitude control devices. So to do this, I'll exemplify by studying a reaction wheel. The first thing we do is drawing a free body diagram of the body, and we show that the torques acting on it are a motor torque and a bearing drag torque. We bring all of this to an equation by applying Newton's second law for rotational motion, in which the first term on the left, the sum of the moments, equals the motor torque as a function of time minus the bearing drag torque, which is proportional to the angular velocity by a constant c. All of this will equal the inertia of the body about its rotation axis times its angular acceleration theta double dot. We will reorder this equation by adding up c times theta dot to both sides of the equation. So in this way, we can leave all of the time derivatives on the left side and the motor torque as a function of time on the right side. Then we will divide everything by the inertia, and thus we get the resulting differential equation theta double dot plus c over I times theta dot equaling 1 over I times the motor torque. So by solving this differential equation, we can get theta as a function of the time, and thus we get a full description of the reaction wheel's rotational movement.
Hello, my name is Melissa Gonzalez, and I will talk about the dynamics and the design of improvements of solar panel arms. It is important to mention that the study of dynamics of mechanisms help us to obtain certain properties that at the same time these properties help us to understand the movement design and its own operation of the system or the mechanism. This through formulas that show us the total mechanical energy, the kinetic energy, the potential energy, and within this we can have the velocities, the mass, the heights. We can see this in improvements of a solar panel arm, like in an example. As we can see, it is a simplification of the problem where it has a constant weight, and at the same time this weight is between two springs with different constants k, and as we can see it has a elastic potential energy, and in the moment 1 it has no velocity, and the moment 2 it has velocity. If we read the formulas, we have potential energy sub 1 equal to the kinetic energy sub 2 plus elastical potential energy sub 2. Then this equation turn in weight multiplied by L equal to 1/2 of K factor of L minus Y squared plus 1/2 of mass multiplied by P squared. And then, like we know that in moment 2 is Y is equal to 0, we have finally W multiplied by L equal to 1/2 of K sub 1 multiplied by L squared plus 1/2 of K sub 2 multiplied by L squared plus 1/2 of mass multiplied by V squared. That's the final equation.
Hello everyone, my name is Matthias. I'm going to continue developing the theme about solar panels. As my teammate Melissa explained, dynamic theory is very useful to get fundamental physics properties like total energy, mechanical total energy, potential energy, and kinetic energy. But also, it is very useful to get more engineering concepts like fuel consumption, power, and the moment made by an arm, a robotic arm, as I'm going to show in my example. So imagine you have uh, an arm that is going up and down, and you need a constant velocity for reason not to damage the structure. And if we use a free body diagram, we can get the m, the moment, equal to weight w for cosine of an angle gamma. Um, Using this, we can obtain the work made by the moment u equal to weight w uh, open parentheses sine of alpha minus sine of theta. So we have the addition of work made by the moment. Down we have other equation where we can find any variable we wish to find with the correct input data. That's it. That's conclude my presentation. Finally, um, what is the common theme in our presentation? What is the common factor between these examples? In all these examples, precision is a crucial factor. If you, for example, reaction wheels calculation are slightly wrong, you can point to a different point in the galaxy. In trajectory analysis is the same. With a slightly mistake, you can have a spacecraft collide between each other. So our conclusion as a team is that dynamic theory is fundamental to the success of any spacecraft mission. So uh, we say goodbye to everybody and thanks for listening our presentation.